Many people mistakenly think resistors act like speed bumps that only slow electrons down. In fact, they work more like traffic jams, limiting how many electrons can flow at once. The average speed of individual electrons usually stays the same under constant voltage. The key to understanding resistance lies in Ohm's law we learned in school. Current through a conductor is proportional to voltage and inversely proportional to resistance. Intuitively, voltage is the force pushing electrons to move. Current is the flow itself, and resistance is what hinders that flow. So resistors are made specifically to provide that resistance. They precisely control current at a given voltage. So why do resistors block current and produce heat? Imagine current flowing through to different materials. One has few obstacles, so electrons move easily with little resistance. The other is full of obstacles, and electrons keep colliding as they move. These collisions not only slow electron flow, but also convert part of their kinetic energy into heat. So, a resistor's essence is to resist current and turn electrical energy into heat. Based on this principle, metal film, and carbon composition resistors are all through-hole types. Their leads make them easy to plug into breadboards or solder onto PCBs. On a PCB, labels like R2 or R3 clearly mark resistor positions, making component identification and placement easier. Look closely and you'll see their internal paths determine the resistance value. A 1 ohm resistor might have a short wide path easy for current to pass. A 100 ohm resistor has a thinner longer path. A 1 megohm resistor has a very thin winding path, giving extremely high resistance. Their sizes also vary. Larger ones have more surface area to dissipate heat. That means they can handle more heat and have higher power ratings. These resistors often have 4 colored bands. This color code shows their resistance and tolerance. For example, the first brown band means 1, the second black band means 0. The third brown band means multiply by 10, so together that's 10 equals 100 ohms. The last gold band means 5 tolerance, meaning its actual value ranges from 95 to 105 ohms. Besides fixed resistors, circuits also need adjustable ones. Common adjustable types are potentiometers and rheostats. They're adjusted with knobs or sliders. Some are tiny trimmers used for fine-tuning after assembly. They usually have 3 pins, 2 fixed ones connected by a resistive track. The middle pin connects to a movable wiper. Adjusting the wiper changes the length of the current path, and thus the resistance between the center and fixed pins. Another type changes resistance automatically with the environment. For example, thermistors change with temperature, photoresistors change with light intensity, and varistors change with applied voltage as electronics get smaller and more compact. Surface mount resistors have become the standard. They're tiny, some can only be seen under a microscope. Their structure is relatively simple. Each end of the ceramic body has a metal electrode. A thin resistive film connects the electrodes. An insulating layer covers the outside. The ends are capped with metal for soldering. To set the value precisely, lasers cut tiny grooves in the film. These grooves narrow the path, increasing resistance. Thanks to this process, SM'd resistors are highly accurate. But their small size means they handle much less power than through-hole types.